Hello and welcome to the second part of the first chapter in Signal Analysis Basics. This is representing vectors as signals, and we're talking about the inner product today. Now, if you remember from last time, we were able to find the magnitude of a vector in the direction of n with this, if we knew what the magnitude and the basis vector or the unit vector in the direction of m looked like, and we knew what the basis vector for n in the direction of n looked like as well. If you remember, that was if we knew in terms of x and y and v and w, we are able to find a of w if we know what w hat is, and we know what x and a of x and x hat is, and a of y and y hat is. So we're able to find a of w, a sub w rather. But now let's move on to actual functions, because as similar as signals are to vectors, they are not vector. Well, they can be represented as vectors, but they tend to be functions of time. So how about we create a function of time? This is f of t and j, a function of, it's a function of time made using the unit step function. And if we draw it on a graph, it looks something like this. When j is equal to 0, the function will have a step function that only lasts one step, and will have a magnitude of 1. So this happens only when j is equal to 0. And you can create others. Say when j is equal to 2, we'll have another step over here. And so on and so forth. Now, how about it, instead of, so let's call this function f of t and j the basis function, because that tells us how the function acts. And let's give it some definition. If we multiply if we multiply that basis function with constants at each place, you can, from vectors there would be the magnitudes of the vectors, but with constants at each point, for each j you have a different constant. So for the first j in this case, this is a constant of 1. For the second j, for v2, this is a so for v0, sorry, this is a constant of 1. For v1, it's a constant of 2.5, sorry. For v2, it's a constant of 0. For v3, it's a constant of -1, and so on and so forth. Maybe we should write those in case you are a little bit, in case you don't understand where I'm coming from. So v0, sorry, is equal to 1, v1 is equal to 1.5, v2 is equal to 0, and so on. Now we can call this function that we have made up v of t. Let's call it that. You can see it's drawn in the orange. It is the sum of all of the v's of j's multiplied with the basis function, all of the constants multiplied with the basis function, In this case, there's 6 of them. So, 7 of them rather. So from here, what if we want to find the kth value? Say, what if I knew what all of the v's of j's were? If I knew what this looked like, sorry, let me see. If I knew what this function over here looks like, v of t, then how do I find the kth element of v of t, v of k? It's not wanting to write. How do I find v of k? Well, how about we multiply by a function that will be equal, a function of k, in this case of t and k, that will be equal, that will, when multiplied with the function f of t and j, will be equal to 1 when k is equal to j, and will be equal to 0 elsewhere. In this case, this is a delta function. This delta function, when multiplied, makes everything equal to 0 when t is equal to k, when t is not equal to k, and equal to 1 when t is equal to k. So in that case, we can find the kth element. But so that there's no misunderstanding here, let's work through some of this. So we have multiplied on this side our function over here, and this side our function over here, and we've done it over all ranges of t so that we can capture any part of t that isn't actually that isn't captured by the sum. So we've done the integral over all versions of t, and whenever t does not equal to k, we'll get a 0, and whenever t is equal to k, we'll get 1. So we will be able to find what our k value looks like. Moving forward, on this side, if we remove everything that doesn't have, if we remove everything from our function that does not have t in it, so in that case this is this part over here, and we move it outside of the integral, then what we will find is this, the next line that has just been shown. And here, if we sum from j is equal to 0 to 6 of v of j, so we know all those v's of j's, but if we multiply that by the integral of this function down here, we will be able to find all the k's. And this function is actually called the Kronecker delta function with respect to j and k. This function is only equal to 1 when j is equal to k and is equal to 0 elsewhere. So that allows us to do something very interesting. It allows us to make this argument that follows next. So when j is equal to k, this function will be equal to 1. So we need to find a place where j on this side is equal to k. We need to make j equal to k, in which case we find our answer. V of k is equal to our function up here. Let me put that in a different color so that it looks different. V of k is equal to our last function down here. Maybe a brighter color would be better. Yes, like a light green color. There we go. That looks much better. So now we've been able to find any some v of k. with respect to our original function v of t. So if we wanted to find the first element, knowing what v of t looks like, then we multiply it by this function. We multiply v of t by this function over here, and what we get is the answer, v of 1. Moving forward, this result is actually very similar to what we found in the last video. If you remember from the last video, if we want to find the constant in a certain direction, then we need to do it. We need to multiply the basis function with respect to both sides, and the function. So we need to multiply the original function and the basis function that we know. The original functions, basis functions, are v of m, and the old basis function, the new basis function, is v sub n. So that's what's shown up there. So it's very, very similar to what we did last time, except this time it's not vectors, but specifically now it's functions that we're working with. This is a very important operation known as the inner product, where it's very similar to the dot product, where you dot two functions together to be able to get a completely new function. There are a lot of important things that we can use with the inner product to be able to find new functions. And the dot product is actually a subset of the inner product. Proving that is outside of the scope of this video, so you'll have to find a video elsewhere to show how that is true. But thank you very much for listening, and see you next time.